Hey everybody, your Friendly Math Tutor here with our Section 2 Part A walkthrough of this AP Calc BC practice test. So on we go to number 1, our first FRQ. These two FRQs are going to be, we can use a calculator. And what we have is a cylindrical tank, and it is the height is, so the radius is always 5, and the height is modeled, the rate of change of the height is modeled by this. All right, so we want to write an expression that gives the volume. So as a function of time. So I'm going to do V of t equals. Now, the volume of a cylinder is pi r squared h, and we know that r is 5 and it's always 5. So that's going to be 25 pi right there. And then we're going to multiply by h. But h is, we have the rate of change of h. So in order to find h, we've got to take the integral. So we integrate from 0 to, well, we want it as a function of time, and we want to be able to find the volume at any time. So if we integrate from 0 to t, whatever t is, that will tell us the amount of, it'll be the change in the height. But since the height is initially 0 because it's initially empty, it'll actually give us the height. Now what I want to do is take this function, and I want to just change it. I don't want to use the same variable as I have up here. So I'm just going to make it an x. And I have 0.05x, x here, and then dx. And that will represent the volume at any time t. All right. So now moving on to part B. So we got the same scenario, and now at time t equals 10, what is the height of the water? Well, we just talked about on part A that the h prime of t, the rate of change of the height, is this function that's given. So if at time t equals 10 I want to find the height, then that is just, say, h of 10 would be the integral from 0 to 10 of this function. I'm going to still write it as x just because I'm going to be putting this into my calculator. But if you use x or t in this problem, it doesn't really matter because there's only one variable. All right, so this represents the change, the net change in the height during the first 10 seconds. Or sorry, first 10 minutes. But again, it's initially empty. So which means it has an initial height of 0. So this actually is the height after 10 minutes. And that is, again, just throw it in your calculator. I use alpha window 4. And then I just type all this in. And you should end up getting 12.359 feet. All right, moving on to 1C. So here we got, as shown, again, we've got the same cylinder. We want to know the rate, at what rate is the volume of the water changing at time t? So what we have from before is that the volume was given as 25 pi times the integral from 0 to t of 2 root x sine of 0.05x dx. And I think it's covered up here. Hold on, let me see something. Yeah, that got covered up here. That's the function. So if you couldn't see that before, it's supposed to be 0.05x. Really 0.05t, but then I replaced it with x. So what we want to do is figure out the rate at which it's changing is the derivative of this. So if I think about what v prime is, then that's 25 pi. And then the derivative of this is the Fundamental Theorem of Calculus Part 2, where you're doing the derivative of an integral. So you're back at the integrand, but at the x's get replaced with t's. So now we're at 2, we'll do it like this. Multiply by 2 root t sine of 0.05 t. And then essentially we want to find v prime of 10. And then we just plug 10 into this. So no integral or anything, you just plug 10 into that. And when you evaluate that, you should get 238.145. That is in cubic feet per minute. All right, let's move on to part D. We want the average rate of change in the height of the water. So average, if I look at rate of change, this rate of change of the height is this function that was given. So if I want the average of that function, I can use the average value formula. The average value formula would tell us to do 1 over b minus a. So the first 10 minutes would be 10 minus 0, which is 10. And then I would multiply by the integral from 0 to 10 of this function, the rate of change. So I'm just going to, again, change them to x's because I would use my calculator, or I'll just take the answer from before and divide by, basically this is the answer to part B. And then I would just divide that by 10. So I should get 1.236. And that is in feet per minute. Or you just evaluate this again, this whole thing again. Okay, so that is the average rate of change of the height. Then it wants the average rate of change in the volume. So I don't think at any point earlier, so we don't have like the function that would give us. Let me think about this. So if we want to take it's the average value. Okay, yeah. So we're basically doing the same thing. We want the average of the rate of change of the volume. Well, the rate of change of the volume is basically 25 pi, because that's not changing, times this. 2 root, again, I'm going to change it to x's, sine of 0.05x. All right, so this right here, what I just wrote out, is the rate of change of the volume, because the rate of change of the volume is just the 25 pi times the rate of change, because the 25 pi is never changing, times the rate of change of the height. So this is the rate of change of the volume. If I want to find the average of that on the first 10 minutes, that's the integral from 0 to 10 times 1/10, and then I'll put a little dx over here. All right, so it's really, one way to look at it is its average value. If you see the average of a function, and here's the rate of change, we can do the average value of that rate of change. Or in another problem, if they ask you average rate of change, you could do kind of like algebra 1 slope concept. So we would do like v of 10 minus v of 0 over 10. But we don't have the volume. But again, when you do that, that is this. All right, so it's just a perspective shift. I'm looking at it from average value, the average value of the rate of change function, as opposed to just the average rate of change of the volume. Okay, so then this is just calculator. And if you put that in the calculator, you should get 97.066 cubic feet per minute. we are on question 2. And we have this polar curve where, if you can't see that, they're telling us it's r equals, I'm going to distribute the 2. 2 minus 2 sine theta. And we want to express x and y in terms of theta. So we start like this. We go x equals r cosine theta. That is just always how x is represented in polar. And then r is 2 minus 2 sine theta. And then that's multiplied by cosine theta. And if I want to simplify that a little bit more, that's 2 cosine theta minus, well, 2 sine theta cosine theta is just the double angle formula for sine. And this is going to help me avoid the product rule. So I am going to leave it that way. So that's x. And then y, I'm going to go up here for y. Y is equal to r sine theta. So y is equal to 2 minus 2 sine theta times sine theta, which means y is equal to 2 sine theta minus 2 sine squared theta. So the first part of this is expressing x in terms of theta and then y in terms of theta. Now it wants dy dx. Well, dy dx is going to be dy d theta over dx d theta. Well, dy d theta is just the derivative of this. Well, the derivative of 2 sine theta is 2 cosine theta. And then minus the derivative of 2 sine squared theta is the chain rule. That is 4 sine theta cosine theta. Because the derivative of sine is cosine. So I'm doing chain rule. Now on the bottom I have dx dt. Well, the derivative of 2 cosine theta is negative 2 sine theta. And the derivative of sine 2 theta is cosine, well, it's 2 cosine 2 theta. Again, I'm doing chain rule. We could definitely get rid of the 2's. So I could just do cosine theta minus 2 sine theta cosine theta, and then all over negative sine theta minus cosine 2 theta. You could make this 2 sine theta cosine theta into sine 2 theta, but I wouldn't waste time with that because I did it before so that I could do a quick chain rule as opposed to having to do the product rule. But now I don't think it's worth it because I have my final answer and I just don't want to waste any more time. So that is one of the answers that we could give. All right, moving on to 2b. We want to find the area of the second quadrant part, the area in the second quadrant enclosed by the x-axis. So that is this little area here. And again, our function is r equals 2 minus 2 sine theta. So the key here is to first know that area would be 1/2 the integral of r squared. So 2 minus 2 sine theta squared d theta. The hardest part of, we got to know that formula, first of all, when you're integrating in polar. And then finding the limits of integration are usually pretty challenging part. So what we want to do is kind of think about, let me think about the best way to go about this. I want to figure out when it's here and then when it's here. Well, it's here when the r is equal to 0. All right, so one thing I can do is I can set this equal to 0. So I can do 0 equals 2 minus 2 sine theta. Add the 2 sine theta over and divide by 2. So I end up getting sine theta equals 1. So that's going to occur at pi over 2. All right, so if we think about this, this thing is going to start here because when I sub in 0, I'm going to get 2. So this is going to be when it's 2 units away, and then it's going to make its way to here at pi over 2. So it's going to be pi over 2 there. And then it's going to make its way over here. Well, over here is when it's equal to 2 again. So I could just, maybe you just know what that is, but in that case, I would want to set this equal to 2. So I would want to do 2 equals 2 minus 2 sine theta. And I subtract 2 and I get 0. So I really want to know when sine theta is equal to 0. Well, that's at 0, but I know 0 is here. The next time it's equal to 0 is at pi. So I'm integrating from pi over 2 to pi. So at pi over 2, it's here, and then it makes its way over here between pi over 2 and pi. And then the rest is just calculator, and you should get 0.712. All right, on to part C. All right, so again, I know this is small. So if we do r equals 2 minus 2 sine theta, that is the function, that polar function that we're working with. It says the x-coordinate of P, of some point P, in the second quadrant is -1. So let's say -1 is here. So here is point P. Then what is the y-coordinate of P? Well, what we know from before is that x is equal to, we did it back in part A, x was equal to 2 minus 2 sine theta times cosine theta, and y was equal to 2 minus 2 sine theta sine theta. So all that is x is equal to r cosine theta and y is equal to r sine theta. So if we know that the x coordinate is -1, what I can do is I can just solve for that in the calculator. All right? I can put this as your x1, or sorry, your y1, my bad. So put this as your y1, I know not this y, like y1 in the TI-84, and then make your y2 equal to -1, because I want to know what input will give me an output of -1. You will get an intersection, and you're looking for the first intersection. So this is if we think about how we trace this out, it starts here, and then it goes here. So this is the first time it'll be equal to -1. So you're looking for the first intersection, and you will get theta equals 2.683. Right? So again, throw this into the y1 with x's in place of theta. You don't want to be in polar. You want to be in regular rectangular. And then make your y2 -1. You'll have a horizontal line go across and find your first intersection point, and your x value will be 2.683. But that x value is really just like our input, which here is theta. And then we want to just throw that in here into the calculator, into that theta, and that will give us the y-coordinate, which should end up becoming 0.493, which makes sense that it's a positive number because we're in the second quadrant. So the y-coordinate is that. All right, so a lot of stuff you could do in your calculator on that problem. Oh, wait. Okay, that's it then. So hope you enjoyed that video. I hope that was helpful. In the next video, I will move on to 3 through 6, which are non-calculator, and that's section 2, part B. All right, hope to see you there.